computer. Good. All right. Hello, everyone. We start with a little slip. I apologize for that. And let's go to the presentation. Okay. So we're moving on in the material, hold on a second. I still don't have the chat on somehow. Meeting controls. Can someone write a chat message? Maybe this will show up on my screen straight away. I guess you did, and it didn't show up. Chat. Alt H. No. Oh, okay. I do have the chat now. I can see the chat now. Okay. Thank you. All right. Let's go. Okay, I can either have my presentation or the chat, which is stupid beyond belief. All right. I hope you see the screen right now that I shared with you, and I don't know how to set it so that I see the chat at the same time. Unfortunately, I somehow figured it out last time, but
if you're in full screen mode, go to the top or see where you can exit full screen mode.
Yes.
And then you should be able to see both.
Okay. You mean exit screen?
Yeah, so like on, at least on my end, when you start the presentation, it automatically goes into full screen mode, and I have to exit full screen mode and then open the chat at the bottom in order to view both the slides and the chat.
Yes, I just don't see how to stop the full screen mode. Screen sharing has stopped, so that's not good. We don't want that. So now I'm sharing the screen, and I go to this slideshow, and I'm see the waiting room and admit everybody from the waiting room. And why is the chat not showing? Okay, yes. All right. Sorry, I see now. Good. Okay. Sorry, everyone. Now I can see my presentation and the chat room. Okay, somehow it worked before, and now it didn't quite. So I don't know. All right. Okay. So what we have today is sets and functions. So chapter 3 and 4 from the textbook. The sections are listed on the syllabus to read from. And I should be posting a homework on the stuff today. That homework will be due on Tuesday. So there is some intersection between end of the first homework and you can start on the homework too. That's because we just extended the deadline on first homework so that to accommodate people who are joining. And yes, that effectively means that you have that you either do homework 1 and 2 at the same time, or you have 2 days less for homework 2. Right. So here is sets and functions. So sets. Set is an unordered collection of items, and we write it in curly brackets. So we if I'm feeling like I'm a little bit lost and I'm going I apologize for that. That's because I'm admitting people who are coming to the class. And hopefully I will set this up better from the next lecture on. So curly brackets denote sets, and the order of elements does not matter. So in here, just a second, I'll switch to, okay, get the laser pointer. So here the order, I can reorder the elements and it does not matter, okay? These two expressions define the same sets. We have a special symbol for denoting that an element, B here, is an element of the set S. The special symbol is this, and it's read is in, or is an element of, okay? So I can just read it, B is in S, B is in set S, B is in an element of set S. And if I want to say that it's not an element, I just cross out this symbol, okay? We can have infinite sets, like for example, set of all integers. And or we can have finite sets, like the sets of students in this quarter of ICS 6D. If a set is finite, then I have special symbols for denoting the number of elements in the set. So here is a set, finite set. It has only 4 elements. And so its cardinality is 4. Okay. Cardinality is, for finite sets, defined as the number of elements in the set. The funny thing is that you can actually talk about cardinality even of infinite sets. These are not integers, though. But we can still talk about them. And for example, you can show that even though integers have infinite number of elements, right? So a set of integers is an infinite set. And a set of natural numbers is also an infinite set. So here are some famous sets, right? Natural numbers, non-negative integers. So 0, 1, 2, da, 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 right? Like round numbers, but 0 included, and positive and 0 including. Z, and it's a special symbol, like N with increased, that side, right? Z is the set of all integers. Q is the set of rational numbers. So a rational number is such that it can be expressed as a fraction where both numerator and denominator are integers, and when you divide, you cannot divide by 0. Okay, so per dual, for example, all integers are part of rationals, because if G is 1, then you just get the copy of integers, right? But there's all fractions. Real numbers, okay? These are numbers which cannot be expressed in this way, like for example, pi or e, right? Or a square root of 3. We can have other like complex numbers and all sorts of other numerical sets. A special symbol for an empty set, you can also denote it with curly brackets with nothing inside. Yes, real numbers include fractions. So these are strict subsets. So natural numbers are a subset of integers. Integers is a subset of rationals. Rationals is a subset of reals. Okay. Oh, good point. Somebody points out irrational numbers also. Okay. So as I was saying, these are all infinite numbers, infinite sets, right? But you can talk about their cardinality. And if you do, then you can show that integers, naturals and integers have the same cardinality. You will see at the end of the class, we'll end with the concept of bijection, a function which is one-to-one from one set to another and also onto. And you can write, just fast forwarding to the end of the class now, you can have a bijection between naturals and integers. It's not obvious what this bijection is, but I can tell you what it could be. This is the 0th element is this, so you map 0 to this one, you map 1 to this, 2 to that, 3, 4, 5, 6, 7, 8, and so on you go, right? And you can now basically see that all integers are covered by a function from naturals, which is a bijection, because everybody is covered here, so it's an onto, and also there's no collision, so it's 1-to-1. So in that sense, you can show that there is the number of naturals and the number of integers is the same, because there is a 1-to-1 correspondence between them. Even trickier, rationals can be covered in the same way. So think about how to do that. It's not immediate. Here, write rationals on a 2-dimensional 2x2 plane. Right? Where for C's along the x-axis, D's along the y-axis, you will have collisions. You will represent same rational twice, but you can eliminate them. And then you will show that you can, the natural numbers are mapped 1-to-1 to rationals as well. Can you do this with reals? I question. All right. Going back to our usual programming, because I'm jumping now. What is a bijection? Not everybody knows at this point. We'll get there at the end of this class. So more on famous sets, right? So we often talk to any numerical domain, like integers, rationals, reals. We can say, we can basically constrain them by saying positive number, like positive integer, positive rational, positive real. Everything greater than 0 in all these sets. Negative, smaller than 0. Non-negative is positive plus a 0. And non-positive is a negative plus a 0. And we can also denote them in this way. So for example, Z plus is a set of all positive integers. N plus is a set of positive naturals. What does it mean? It's basically naturals, but you kick out the 0. What is N minus? It's an empty set. All right. So this, you can apply this to, of course, the natural place to apply it is not when A is equal to N, but when A is Z, or A is Q, or A is R, right? So integers, rationals, and reals. Here's 2 ways in which you can specify a set. There is a roster notation. Just list them, right? So if your set is finite and small, that's a convenient way to define a set. Here is a set of all odd integers between 1 and, smaller than 10 and positive. You can also list a larger set, right? Which will be annoying to write it, right? Like, as long as the pattern is inferred, right? So here is a set 1, 3, 5, 99, set of odd numbers. And, basically every human after first grade of elementary school will basically say, oh, okay, this is odd numbers, okay, smaller than 100. And this is odd numbers in general, right? Look, but use it, here is some pattern, okay? And basically nobody knows what this pattern is, right? I mean, it happens to be this one. It's all integers of the form of square minus 1, right? So now that I told you this, then you can check. Yes, these are all squares minus 1. But, it's not a good way. I mean, people are not going to understand you when you write this. Although I guess you can write it on some sort of test in arithmetics, like a quiz or something. Set builder notation. So a different way to define a set has this meta form, okay? This basic form. In the curly brackets, you start by defining what the elements are. And this is read such that And here is some condition on these elements, some constraint. Like, for example, that they all belong to some set, perhaps with some additional conditions. Perhaps what you have here is a Boolean formula. All elements which satisfy some Boolean formula, right? You could do that using the stuff from last week. Or more generally, you have on this side, you specify a function of some arguments. And on the right side, you specify constraint on these arguments. So you read this like this. This is a set of all elements of the form f of x, where f is some function, and arguments x have to satisfy such that x satisfies some constraint. Like, for example, it belongs to a set S. So let's give examples. Okay. So here, I define a set of elements of the form n squared minus 1. That's a function whose argument is n. So these are this is a set of elements n squared minus 1 such that n is a positive integer. So it's this set, except that now it's well defined so that everybody can actually understand what this set is. Another example, n such that half of n is a positive integer. What is that set? Well, it's a set of even positive integers, right? That I just defined here. Here, a set of elements of the form 2n such that n over 3 is a positive integer. So if n over 3 is positive integer, then what is 2n? Well, it's basically 6 times some positive integer. So that set is basically positive integers divisible by 6. And or n squared such that half of n is an integer. So what is this? It's a set of squares of even numbers, because this thing basically defines even integers, right? Okay. Subsets. So you have two sets, and you say you define a relation on sets. Excuse me. The relation is a subset, not a relation. So two sets have this, are in this relation that T is a subset of S if the following statement is true. For every X, no matter what this X is, if that X is an element of set T, then it must follow that it's also an element of set S. Somebody wanted to ask a question? Okay, maybe not. Somebody unmuted and sounded like wants to ask this question. All right. So for example, you can represent it as a Venn diagram, right? So here is a set S, and here set T is a. So whoever unmuted themselves, if they don't want to ask a question, could you mute yourself, because I hear you rustling some papers. So because it's so if you want to show, so first of all, if it's not the case that set T is a subset of S, we denote it with the subset symbol crossed out. So this holds if this is not true. And look, if I'm negating a statement like that, if I want to show that the negation of this is true, what is the negation of for all? That there exists X such that this is not true. And now what is the only case that an implication is not true? It's the case where the first part is true and the second isn't. So I have to show you that there exists an X such that it's in here, in T, but not in S, right? So here you have it. So to show that the two that T is not a subset of S, I have to just show you a single X, which is in T, but outside of S. Let's look at an example. Here are the 4 finite sets. And let's ask, what's an element, which one is a subset of which. And so here is T is indeed a subset of S, because all these guys are also members of the set S, right? It is the case that whenever X is in this set, and that happens if and only if X is either A or B or C, then X is also an element of this set, right, as you can see. Now, what if, is this V a subset of S? Is it true that for all X's in here, they're also in here? And then there is no, this guy, E, is not in here. Okay, and likewise, V is also not a subset of T for the same reason. E sticks out. Okay, so let's define operations on sets. Okay, and these operations correspond basically one-to-one to Boolean operations. Here is a union. We define a union of two sets with the following set builder notation. So look, the left-hand side here is a definition of a set. It's a set of X's such that, okay, and I define the set in such a way. A disjunction of two statements must hold. So it's either that X is in set A or X is in set B, and that defines A union B. So here is that, if this is your two sets, A and B, the black stuff corresponds to a union, right? So this is all the elements in this set and all elements in here. This is the union of A and B. Intersection is defined using a conjunction. So an element belongs to an intersection if and only if it is the case that it belongs to A and it belongs to B. So graphically, intersection is this little sliver here. It's everybody who is both. This is the set of elements which are both in A and in B. So somebody asked on the chat, what about proper subsets? Well, that's not a set operation. That's a relation between two sets. And proper subset, so we say A is a proper subset of B if it is the case that A is a subset of B and A is also not equal to B. So it's a non-trivial subset. Okay. All right. Okay. So somebody else on the chat, what's the difference between inclusion and membership? We will get, they are different, and we will see this, a bunch of examples in a few slides. Set difference, another operation. It's a set difference is defined as all elements which satisfy this Boolean formula. So it must be the case that both X is in set A and it is not in set B. Okay, so graphically, it's everybody in A minus B, set minus B, is everybody who is in set A, except if they also belong to B, which basically means that you're kicking out this fragment of set A from it. By the way, I don't remember now, but I think the book might use just a standard minus for set minus, right? So there are people who use the same minus as over integers. I mean, right, like a numerical minus operation. And we also use this operation. So I use this one. I think the textbook uses minus, the standard horizontal line. Both are okay. You can use either one, but for God's sake, consistently, right? All right. Complement. This is an operation denoted with a bar over a set. And when I write a barred, that defines a set of X's such that this formula is true. So therefore, there are all x's which fail to be in A. Now, for this to make sense, you have to define some notion of an implicit universe, right? Because let me give you an example. When I say, okay, what is a complement of students in section A? Well, like a normal person would be like, well, these are students in section B, right? These are not like all students at UCI, or all students in the world, or all objects in the world, right? Like including birds and fishes, right? So basically, to properly define a complement, I have to have a notion of what the universe is. So here I have a universe is everything in a square box, and I kick out people in A, or I get the rest of the universe. Let's do some examples. Here's a set using the set builder notation. These are all, oh, in fact, this is a little variant of the, this does not exactly fit the form I gave you, because on the left-hand side, I don't have a function. Sorry, I have a specification of the domain already on the left-hand side. You can do that too. So how do I read this? A is a set of all x's in the set of integers such that x is an odd. Odd is odd, right? So A is a set of odd integers. B is a set of integers x such that x satisfies this constraint. So it's an integer between 0 and 10, not including, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the set B. And C is a small set defined explicitly this way. And assume the universe is all integers. Okay, let's see. What is, and let this be our cheat sheet, right? Like these are the definitions of what these things are. So let's see, what is the intersection of A and B? It's a set of all elements which satisfies this conjunction. It's an element that is both in A and in B. Okay, who is in A? Odd integers. Who is in B? Integers from 1 to 9. So who can possibly satisfy both of these? Well, integers between 1 and 9, which are also odd. So it's this, right? Okay, what about C and a complement of A, right? What is a complement of A in the universe of integers? So A is all odd. What is a complement? Everybody who violates this constraint, right? That's a complement of A. So how do you violate being odd? Well, you're even. That's the only way, right? So, so now, good. Somebody put it on chat. Exactly. So these complement of A are even numbers. So you look at the intersection. You have to be even because you're in a complement of A, and you have to be in C. So here, and these are the only possibilities. Question: is this a subset of that? Well, and yes, right? Because all these numbers satisfy this constraint. Oh, I don't have a cheat sheet for what an inclusion was, but it corresponded to implication, right? So this
question.
Question.
Sorry, quick question about C and the union of. Sorry, C and what's that symbol? Oh, it's a C. A complement of A. Okay.
I see. On my cheat sheet, I'm missing the complement.
Oh, intersection.
I didn't copy the complement. My cheat sheet
okay.
has a typo here. That's
okay,
assume you'll be adding that.
Say what?
I assume you'll be adding the missing part in the cheat sheet later.
Yes, if I remember, but yes.
Oh, I think I see what you did because C has 4 and 6 and then intersection. Okay. Intersection of a complement.
Complement of A is even numbers.
Yes.
Right. So that's why the only even numbers here are 4 and 6.
Right.
Okay. And this here misses the complement sign. All right. So what was the inclusion formula? This is true if and only if every element that belongs to C. If X belongs to C, then X also belongs to B, and that's true for all, right? Because X belongs to C is satisfied only for these four numbers, and all of them satisfy this constraint. Okay, now, sorry, so is B a subset of A? So is it true that for every X, if X is in B, in other words, if X satisfies this constraint, then it also follows that it's in A, namely that it satisfies this constraint. And that statement is not true because it's not true for all the even elements in here, right? So for example, 2 is in here and it's not part of set A, right? There are other counterexamples, 4, 6, and 8. Let's look at more complex formula. So what is a complement of the union of A and C? Okay, so you take a union of A and C. What is it? A is all odd numbers. These are numbers that satisfy either you are in A or you are in the other element of the union, right? Which in this case was C. Of course, it's also fine if you're in both. So these are all odd numbers plus 4, 5, 6, and 7. Now, adding 5 to a set of odd numbers didn't do anything, right? It still remains a set of odd numbers. Adding 7 to a set of odd numbers also didn't really change it. But adding 4 and 6 will amend this set, right? So a union of A and C is all odd numbers and also 4 and 6. And therefore, the complement does not include 6, right? Because 6 is in the set, so it cannot be in the complement by this formula once you put the complement sign missing here, right? You can also do it quick because in fact you don't really care what say A is, right? You know that 6 is in C, and you also know that whoever was in C is also a member of this union. Does not matter what A is, so therefore it cannot be in the complement, right? All right, what about 26? Is it in this complement? And you can be like this, okay, how can you be in the complement? Well, you have to be not inside here. Is 26 inside here or not? Is 26 an odd number? No. Is 26 one of these? No. So therefore it's not in the union. So therefore it is in the complement of the union. Yeah. Okay. Power set. Power set is, okay, consider a finite set. Okay, you can define power set over infinite sets, but we won't for now. The power set of A denoted using this special symbol, okay? It's P of A. It's like a function, okay? And when I know that this is a set, then I will read this expression as the power set of whatever the set is. It's defined to be the set of all subsets of that set. Let's look at the example. Let's take a set that contains 3 elements, A, B, C. What is its power set? In other words, what are the possible subsets of this set? Well, there's 8 of them. An empty set is always a subset of everything. Why is that? Because it is the case. So how can you test that an empty set is a subset of this set? Ask yourself a question. Is it true that every element that belongs to this set is also a member of this set? Is it true that if X is here, then it is here? Well, that statement is true. Does not matter what the set is. Why? Because it's an implication. And if the first part of the implication is false, because X is not in this set for any X, there is no X, which is here. So a statement that says, if X is here, then, well, this statement always has a false precedent. So the antecedent of the implication is always true. Okay, this is a subset of this set, obviously. If this is a so-called singleton set, it's a set that contains a single element. It's a set whose only member is A. So the implication is for every X which are in here, Is it true that there is also in here? Yes, it is true. There's only one X in here. His name is A, and he is here. And the same goes for these two. And here are another subsets, right? These are the subset made of any two of these. And here is a subset. That's a trivial subset. A set A is always its own subset. Because if you look at what is the subset equation, let me bring this up. Maybe I shouldn't have. Here, T is a subset of S if the following implication is true. For every X, if X is in T, then it's in S. Now put A here and A here. Is it true that A is a subset of A? Is it true that if X is in A, then X is in A? Well, obviously, yes. Right? So that's why a set is always a subset of itself. And if you look at the set, if you were amending this by saying, okay, let's look at all the proper subsets, which there will be only one element less. You kick out this. And the rest is the set of proper subsets of A. All right. Now, so is, go to your charts and tell me what's the answer here. Is this thing, which is a set that includes, this is defined, this thing is a set. It has this, it's a set of just two elements, A and B. Is it an element of this set? Where this set, everybody says yes, and that's correct, right? Because where is this thing in here? It's this, right? P of A is a set of sets. Members of P of A are sets. All of these things are sets. Here's an empty set. Here is a set whose only element is A. Okay, good. Is this true? That this set is included in the power sets of A. Okay, so I think I have diverse opinions on that. So let's check. What does it mean that?
Sorry. I forgot to unmute myself. Sorry.
Okay, sure. No problem. All right. What does it mean that this thing is a subset of power of P of A? It has to be true that for every X, which is a member of the set, it's also true that it's a member of the set. What are the X's which satisfy being members of the set? There are only two of them, X equal to A and X equal to B. Let's take X equal to A. Is X equal to A any of these things? And the answer is no.
What about that one right there?
Yes. So no, this is a set whose only member is A.
Oh, you don't
okay, it's not A itself.
Okay,
like,
so that,
you know, of course, what does it mean in real life? You know, when I say that here's a set of students, of professors at UCI whose first name is Stanisław and last name is Jarek. Well, that set includes only me. Okay, so why don't I just say, here is just Stanisław Jarek, right? The thing is that it matters. These are basically levels of abstraction in programming. So if you just think like, okay, is there no difference between a list that includes, that has integers, and this list has only one integer, and the integer itself? Are these the same objects? And basically, when you program, you know immediately the answer is no. These are two different objects. Like if one guy codes it and says that, you know, it codes it as lists, and these lists include only one element, and you know his colleague, she implemented like just as integers themselves. these two pieces of code are not going to communicate. They have different objects, right? So here is one, a sphere of life with which you are familiar, where these things matter, whether you talk about an object or a list of objects or a set of objects. And even if that set includes a single thing, that's not the same as that single thing, right? And it's not the only application of sets, right? But that's the one that we are very familiar and intimate with. All right. So again, this is really the same question. That's precisely why I said this is not true. If you instantiate X with A, it is not true that it's a member of the set. So that was our counterexample for why this set is not included in here. It's a member of it, but it's not. These two sets are not bound by an inclusion relationship because precisely A is not a member of the power set. This set, whose only member is A, is. Okay, so the answer to this question is yes. I'm sort of beating on the same horse all over here, right? But just the different ways to say the same thing, right?
Okay, I see.
Once you understand one of them, then you understand the other. It's one and the same thing said over and over. Now this right? So is this set a subset of this one? Is it true that for any X which is good, and there's a bunch of yeses on the chat, and that's correct, is it true that every element of this set is also an element of this set? Yes, it is true, because the only element of this set is this thing. It's a set whose only member is A. And is that an element here? Yes, it is. Here it is. Okay. So, and in fact, we checked it right here, right? So.
Wait, how are those two equivalent, 4 and 5? Because isn't that saying a subset of a subset, or like?
No, they're not equivalent, but 5 follows from 4. Because for this to be true, the following implication has to be true. For every X in here, it's a member of the set. Now, the only X in here is this X. It's the X which is a singleton set whose only member is A. And I already established that it's a member of the power set. Therefore, I'm done. I don't have to check, right? It just follows by 4. All right. A 0 is an empty set a subset of this power set?
Yeah.
Yes, right. And why? Because basically, because this implication holds for every, I don't even have to look at the right side. An empty set is a subset of every set. Because the implications that for every X which are in here, whatever something happens to them, I don't care what that something is. The implication would be true because the first part of the hypothesis in the implication is always false. Is an empty set a member of the power set? And it is the case. Somebody asked on the chat why this is false. Because of this. Because take any guy in here, like for example A, and it's not a member of PA, right? This thing is a member of PA. Set whose only element is A, but A itself is not. Okay, so a little bit of this type of you're gonna be, you will have to do stuff like this. Okay, we have to get used to it. You can protest like, why on earth am I doing this? Who cares how these things are defined? Well, they're basically practicing ability to abstract and ability to tell between members of a list, a set, a collection, and collection itself. Okay, and if you don't think that this stuff is useful, think about data structures that are records or lists. and that include other lists. So these are sets of sets. Somebody has, is an empty set equal to the set whose only member is empty set? No, it's not equal. You can tell that what's the cardinality of this object on the right hand side? I don't know if you all can see it. The cardinality is 1, and the cardinality of an empty set is 0. They are not the same. And the second question that Christian asked on the chat is true. Empty set, it is just different notation for an empty set. Here is sets are not everything. There also, it makes sense to order things. So sets are unordered, and the set of A and B that includes A and B can be written in that way, or it can be written in that way, and it doesn't matter. With round parentheses, we denote sequences which are ordered sequences, and here is just sequences of length 2. So it's a sequence that has 2 elements, A and B, and we declare it as a different object than a sequence that includes B and A. You know, think of a list in a data structure, right? It's obviously the order matters, right? So you can have a sorted list and you can have an unsorted list. ABC is an ordered triplet, right? And I can talk about the second, third, so-called element of the sequence. And for sets, it makes no sense to say second element in a set, right? Because sets is unordered. Or an ordered 4-tuple, or in general, basically an ordered N-tuple, which is an N-element sequence. Okay. Cartesian products. So I can take 2 sets, and by a Cartesian product of 2 sets, denoted by this type of product symbol, it's a set of ordered pairs such that, so here is a set builder notation. What is that object? A Cartesian product of set S and set T. It's a set of pairs, ordered pairs, I mean pairs which are ordered, of 2 elements, S and T, such that S is a element of set capital S and small t is a set of set capital T. So for example, the first set is has 3 elements, A, B, C. The second, 2 integers, 1 and 2. A Cartesian product of these 2 sets is a set, right, of all pairs such that the first element in the pair is in this set and the second is in this set. Okay, so there are 6 such elements: A1, A2, B1, B2, C1, C2. By the way, right, because you will basically form in a Cartesian product of 2 sets, you will have every combination of element in the first and element in the second. So how big is the Cartesian product of 2 sets? What is the cardinality of this set? It's a product of the cardinality of this of S and the cardinality of T, right? Because every matching between them is a member of S and T, and they're all distinct. Hence, it's basically called a product, right? It corresponds to notion of product when you think of their cardinalities. So let's take T, a set of 2 integers, 1 and 2. What is Cartesian product of T with itself, which I can abbreviate as T square? It's a set of pairs such that first element is in T and the second element of T. These are all these pairs, right? There's 4 of them because the cardinality of T is 2. Is this set included in this one? No, because syntactically, this is a subset of integers, and this is a subset of pairs of integers, and there's no integer whose there's a pair of integers at the same time, right? What is R square? it's a set of pairs of real numbers, z square, pairs of integers, and so forth. Think you have I can do Cartesian products of many sets. They are basically set of triples whose elements are the first element of this Cartesian product must be a member of the drink set. The second element, a member of the main dish set, and the third element, the member of the last set, right? So this Cartesian product, how many elements it will include? Where there's 2 possibilities for the first, 3 for the second, and 2 for the last. It's a product of the cardinality. So it's 2 times 3 times 2, right? 12 possibilities. And you can think of them, basically these are records think of them as records as a data type. If AIs are sets, then a cross product of these n sets is a set of sequences of the form x1, x2, xn, such that xi in here is a member of set AI, and that has to hold for I ranging from 1 to n. So for example, x1 must be a member of A1, x2 a member of A2, etc. Right? So this is a generalization of the formula we already have. So you can do it with a set itself, right? So you apply this definition when all the AIs are equal to the same set. So a set to the nth power is a Cartesian product of a set with itself n times. What is it? These are sequences of n elements such that each of them is in set S. Okay, and why would this be useful? Okay, think of what's a Cartesian product of a set. What is this set? It's our beloved set of bits. Okay, it has only 2 elements and they are bits, 0 or 1, right? And when I take a Cartesian product of this set 3 times, what do I get? I get sequences of 3 elements whose first, second, and third are all members of the set, which is a set of bits. In other words, these are sequences of 3 bits. Okay, so if I want to define, say, look, my code works on inputs in the following sets, and when I want to say 128 bit strings, I can say this to the power 128, and that will define a set of 128 bit strings. It's a concise, useful notation. R4th, what is it? It's a set of 4 tuples, each of which, x1, x2, x3, x4, each of which is in the set R, so these are all real numbers. So there are the length 4 sequences of real numbers. Okay. Now, instead of thinking them as n tuples or sequences of n length, I can think of them as strings. So here is a good notation, sort of not convenient, just a usual notation for a set of, when we define an alphabet. Like, for example, when you explain what a Turing machine is, or yeah. So this is a sigma, Greek sigma, capital sigma. It's a set is an alphabet. Let's say single characters in ASCII, okay, and let's say just lowercase. So elements in sigma to the n. So this is a Cartesian product of sigma with itself n times. So what are they? These are n long sequences whose every element is in sigma. Therefore, they're basically n tuples of sigma. They are strings of length n whose every character is an element of sigma. Okay, so for example, if your alphabet is very tiny, it's just A and B, I can describe elements of sigma to the fourth the way I did on the previous slide, which would be a sequence of 4 elements, each of which is in here. So for example, this sequence is in this set, right? And so is, how many sequences are here? 16, right? Because there's 2 possibilities for the first, 2 for the second, 2 to the third, 2 to the fourth. And by the way, this is why also this has a good notation. It looks like an exponentiation, because if you look at the cardinality of this, it is indeed the cardinality of this alphabet to the 4th power. Or I can just ignore brackets and commas and write it this way. And this is the string notation. And this is just a different notation for elements of the set. So look at the bit strings, right? I don't write bit strings as 0, 0, 0, 0, 0, 0, 1. No, I just write them as 0, 0, 0, 0, 0, 1, etc. Right? And but I can do this for every alphabet. Indeed, when my alphabet is ASCII, I can write a word like binary, right? And where is this word from? It's a 6-tuple of where every element is a small, it's a lowercase English letter, right? So my sigma here could be lowercase English letters, or it could be ASCII. So you don't use punctuation if if these things have, if these are single characters, right? If sigma includes strings by itself, then perhaps, okay, then this would be an ambiguous notation. Another common operation on strings is concatenation, and not another. There's the first operation on strings I'm defining. If X is a string abba and Y is a string bab over the same alphabet contain just A and B, then I can write the concatenation of these 2 strings in this way. Okay, just follow X followed by Y, and it's going to denote this string. Okay, so it's a string over 7 long sequences of elements whose every element is in this alphabet. Or I can, denote an element here itself, right? So this is a string of length 1 in this alphabet, right? And I can, yeah, and the concatenation will look like this. I can denote concatenation like that or like that. This is a notation that is used just to stress, right? Because if you're not sure what X and Y are, perhaps they are integers, then this stands for integer multiplication, right? But if I want to draw your attention that X and Y are strings, then I will use this notation. And there is a special symbol for empty string with no characters. So the only strings that satisfies this relation. If I concatenate any X with lambda, I get that string. And if I concatenate lambda with that string, I get that string back. Okay, and the length of the string is denoted also with the same, it's the exact same notation as cardinality of sets. And it's not my fault. It's just true. We use the same notation for cardinality of sets or length of bit strings. And you have to know whether the X object is a set or a string in order to know what that thing means, right? It is the same notation. It's not just something I came up with. And you have to disambiguate it when you read these things. So somebody asks, are strings treated as tuples? Yes, they're equivalent, right? So strings have you can think of them as tuples, as sequences, or you can think of them as strings. You think of them as strings if they are sequences of in Cartesian products of sets which are identical. So it's the same alphabet sigma at every index in the sequence, right? All right.
Are strings supposed to be ordered, right?
Oh, yes. Strings are ordered because they are equivalent to sequences which are ordered. The infinite set of strings. So look, let's say sigma is an alphabet. I have a special symbol, sigma star. Not sigma to the 0, not sigma to the 1, not sigma to the 2, sigma to the star. It's a special symbol, and it's defined like this. It's a union of sigma to the 0 and sigma to the 1 and sigma to the 2. What are these things here? What is this? This is the set of sequences, or think of them as strings. Strings over alphabet sigma of length 1. This is set of strings of length 2 over alphabet sigma. And what is this? This is strings of length 0 over alphabet sigma. So no matter what sigma is, sigma to the 0 is made of only one element. It's an empty string. That's the only member of this set. This set, for if let's essentially sigma is bits, right? So sigma is set of two elements, 0 and 1. What's sigma to the 1? It's these two guys, right? These are the members of this set. These four, from 0, 0, 0, 1, 1, 0, 1, 1, these four elements are members of this set. And you know, I didn't list all the members of sigma cube because there's already 8 of them, and so forth, right? You also have a special notation for all substrings. So what is sigma star? These are all substrings over this alphabet. So sigma star, when sigma are bits, denotes all bit strings. Yes? And sigma plus are all sequences of any length except the empty string, right? So I just kick out this element. In other words, sigma plus is sigma star minus a set who contains only an empty string. Okay, so these are useful notations because you can say, you know, set of all bit strings. Okay, function. Function is okay. So this is, you know, you know what a function is, right? But let's just recall. A function is a map that between two sets. F is a function from set A to set B, denoted like this. If, first of all, A is some set, and that set is called the domain of function F. B is another set, and it's called the target or codomain of function F. And a function is a correspondence that for every element of A, it assigns to that element some value in set B. So here is a graphic way to represent a function. If I have finite set A, in this case, a set A, excuse me, is a set of 4 elements, A, B, C, D, and a finite set, a finite codomain, five elements, 1, 2, 3, 4, 5. This is a function, and to evaluate a function I can evaluate it on any argument. If I evaluate f of A, that's a 1. If what is f of B, that's a 4. Also f of D is a 4. F of C is a 2. There is a concept of a range of a function, and I don't have this on the slide, but it's denoted by f with with an arrow on top. Okay, so that's a okay. I cannot write this right now. I can write it like this: vector f of a. This is range of f of function f on domain A. And it's a subset of the codomain. So in this case, the range of the function, the range of function f is a set made of 1, 2, and 4. Okay, but 3 and 5 are in the codomain, but they are not in the range of f. Okay, functions are often specified by an explicit formula. So here is a function that maps reals to reals. The formula is f of x is defined as x squared minus 4x plus 3. So I can evaluate this function on any real. So x is some real. And how do I evaluate it? I evaluate this formula. And that defines what an f of x is, right? Here is some example of f's which fail to be functions, right? So these are not functions from reals to anything. Like, for example, plus minus square root of x. That's not a function because for two reasons. First of all, not everybody in reals have a square root. Negative numbers don't. So this formula fails to define any value for half the domain, right? On the negative reals, it wouldn't define anything. There is a second sin that this expression makes, and it is that even for the positive ones, when the square root is well defined, what do you mean by plus minus? So you assign now 2 values to this function. So on argument 4, square root is true, but how do I evaluate this function? Is it a plus 2 or a minus 2? I don't know. I don't know how to evaluate it. And it's so the property of a function is that the value of the function must be unique. It must exist, number one, for all elements in the domain, and also must be unique. So it cannot be that a function defines 2 values for the same argument. On the other hand, it's okay if the same value is the value of the function on 2 different arguments. That's not a problem. Here is another failed definition. So why 2 over x fails to define a function on reals? Well, it's almost good, but it's just 1x for which it fails is x equals 0, right? This division is undefined if you try to divide by 0. So, okay. Okay, I forgot that I had the answer here animated. An important concept in function terminology. We call a function one-to-one, or otherwise it's known as an injection, if it has the property, if it satisfies the following property, namely, for every 2 elements, x and x prime, in the domain of the function, the following implication goes true. If x and x prime are different elements of the domain, then necessarily must follow that the value of the function on x is different than the value of the function on x prime. So this thing fails this, this function fails this, do I have it animated? Yes. This function fails this predicate, this constraint, because if x is equal to b and x prime is equal to d, this part is satisfied, so therefore this must be true, but it's not. F of b and f of d are the same value for. So it fails this, and it's not a one-to-one function. In other words, it has collisions. That's a fast way to say, right? And visually you can see what a collision means, right? So function is one-to-one if it has collisions, and it's if it does not have collisions, and it's one-to-one if it doesn't have collisions. And here is an example of such a function, right? There is no element in the range which is mapped to by 2 different right? So this function does not collide. These arrows never meet on the right side as these two arrows did. So that's a notion of injection. So here are the examples. So is this a one-to-one function over the reals? We don't have a lot of time, so I mean, basically no, right? Because -1 and 1 have the same square, right? So minus x and minus x have the same square, right? So they violate the implication that if x is different than x prime and take x prime equal to minus x, then the value must be different, but it's not. Minus x and x always have the same value. Fx equal 2x plus 3 is a linear function and it has no collision, right? So if you draw it over the two-dimensional plane, it will look like this. So it will have no collision, meaning for every y, there is only a single element, right? Why does this have collisions? Because if you draw it, it looks like this. So for the same y value, there's two different elements that satisfy this equation. Let's consider a function of bits. It assigns to every length 3 bit string another length 3 bit string. How? By replacing the last bit with a 0. So this function takes any 3 long bit string and flips its last bit. So for example, this. Is it one-to-one? Okay, does it ever collide? Does it ever create the same bit string in the same way? And no, right? Because basically, why can you convince yourself that does not collide? Because you can invert it. Because if you give me a value, I can flip it back. And it's also a function that inverts this function, right? So it has no collisions. I mean, you can also just convince yourself that it has no collision.
Quick question about that function. So this function is replacing only the last element, which
Yes.
or the last element, which is like, let's say if
Oh,
f11 is going to be 0.
sorry. So, yes. I was saying different thing,
Okay.
and what I'm writing is a different thing.
Okay.
Yes. So
Yeah.
in my speech, I give you an example of a function that flips a bit, and in the writing, I had it right in front of me. No, it's a different function. And yes, you're completely right. This function, as written here, it's a function that just zeroes out the last bit, and obviously it has collisions, right? This bit string and this bit string, these two bit strings, will have this value, right? Sorry.
Yeah, it's fine.
Yeah. All right. So let's have a different function. Take a length 3 bit string and create a length 4 bit string by just adding a 0 at the end, right? Like this. So that one will have no collisions, right? So it is one-to-one, because just these first 3 bits will be different for every value. Or take a set and assign, let f be a function that takes what is this function? It's a function whose domain are elements of the power set of A. In other words, they are subsets of A. And to every subset of A, it assigns an integer, namely its cardinality. Okay, so it's a function that maps subsets of A into their cardinalities. Does this function has collisions? Yes, because every singleton will be assigned the same cardinality, 1. Right, and every subset of 2 will have the cardinality 2, and there's many of them. Yeah. Okay, corresponding, so the flip notion is an onto function. It's called surjection. The function is onto if the following implication is true. For every element in the target, there exists an element in the domain that gets mapped to that target. So for example, this function is a surjection because every element y in the target, it is the case that for every element there exists somebody in the domain which maps onto this y, right? For this guy, it's true that there's both, but it doesn't matter. It exists, okay? And it exists for all of them. But here, it is not true, right? The 3 is not mapped by anyone. So function is surjective if every element in the target is mapped by someone. Okay, and here are the example of surjective function. So I'm sorry that I stayed a little longer. This is we're only 2 slides till the end. So if you bear with me, that's all that it will take. Here is the same function as before, right? So let's look at if there are onto. Is this function onto reals? No, it's not, because it gives squares and therefore positive numbers. So negative numbers are not mapped, right? There is no negative number in this target that is a value of any reals that has this form, right? Now, let's look at this one. It's a function from integers to integers of this form. Is that an onto function? So is it true that every integer has this form where x is an integer? No, right? So there is going to be integers which are not of this form where x is an integer, right? So take 2. 2 that cannot be represented this way, okay? So, I mean, okay, you can convince yourself at home that this is the case. What about if I change the domain and the codomain? I think of the same equation as a function from reals to reals. Then it actually, I don't know what happened with the, okay, it is onto, okay, right? Because every real is of this form where x is some real, right? So this function is over rationals. This will also be an onto function. What about this bit zeroing? Does that operation, is that operation onto? No, because any string that ends with a 1 is not it's not in the range of this function, right? So this function is not onto. And if you remember, it wasn't there's a 1-to-1. What about this function? The function takes a 3-bit string and drops the last bit. Well, that function is onto, right? So every 2-bit string is some 3-bit string with the dropped bit. It's actually 2 different, but I don't care. Some elements are mapped onto this, right? Or make a funny function, take the last bit, remove it, and put it at the beginning. Rotates the string. It's onto. Okay, well, why? Because you can invert it, right? So that's another reason that, so that brings me to the notion of bijection. Bijection is a function which is both one-to-one and onto. And it is not on this slide, but the sort of key concept between a bijection is that it can be inverted, right? And here is why it can be inverted, because if a function f from g to t is both one-to-one and onto, can I invert it? Is the inverse of this function well defined? And I say it is, because for every t, there exists some x in here. For every y, for every value in t, there exists some x in the domain that maps to it. Why do I know this? Because it's onto, right? Everybody in this set is mapped by 1. And is it unique? Yes, it is, by one-to-one property. So therefore, every y is mapped by a unique element in here, unique x. That's how you define an inverse of the function. An inverse of the function is a function from t to d such that the value of this inverse of this function on element in the t is a unique element in t which f maps to it, right? So it's very easy on the graph, right? When I have a function that okay, except that I don't have, you know, if you skip the a here, if you pretend that the subset is just BCD, then an inverse of this f function would be just invert the arrows, right? Because then 1 would map to B, 2 to C, 3 to D. Here is an example of an invertible function, this one, right? this function is both an onto and a bijection and one-to-one, because it's invertible, because I can inverse this operation, right? I can take this first bit and move it back to where it came from and get back the string from it uniquely, right? So this is an example of an invertible function. This is also an invertible function, right? And so on and so forth. And then this just go back to the beginning of the talk, where I talked about bijections between, let's say, all natural numbers and all integers. So they can be placed into a bijection. It's not obvious, perhaps immediate, how to do it, but once I show you, right, it's like, oh, okay, yes, you can have. And why is this a bijection? Because every every integer is mapped to uniquely. There's a single natural number that mapped to it, and every integer is mapped by some natural. Therefore, it's a bijection, and therefore the cardinality must be the same, right? So even if these sets are infinite, I can basically say, okay, the number of natural numbers and the number of integers is the same, which is odd, but once the sets are infinite, it's possible. Okay, more to read in the text. Homework coming up, and now we move to okay, and we move to questions and answers if anybody wants. Speak up.
One question.
Yes.
About onto and one-to-one. They are not invertible, but only bijection are invertible.
Yes.
Okay.
Yes, you have to be a bijection to be invertible. Now, yeah, yes. So yes. So this function, if I kick out 3 from the codomain, then if I declare the domain of the the codomain of this function as the range, so it's just 1, 2, 3, and 4, and 5, then it becomes a bijection. But if this guy is included in the codomain, then it's not a bijection because it's not onto. It's one-to-one, but not onto.
Yeah.
Other questions?
Hi, Professor.
Homework is up, right? Is the homework up?
No, homework on part 2. No, I didn't put it up. You will get a Piazza email when I commit it.
Okay, so it'll be due on Tuesday of the following week?
Yes. Even though the first homework is due on the Thursday, was extended.
So it'll be due on 21st?
I don't have a calendar. It's due in a week. No, it's not 21st. It's +7. Today's April 7th. It will be due on the 14th.
Oh, that's the homework will be available by when?
I release it Tuesday. It's due on Tuesday. You have a week for every homework.
Okay.
Yeah.
Professor, could you
Yes.
please go back to the slide of range and codomain? I missed that.
Yes. This one. This one?
Yeah, thank you.
Mm-hmm.
So codomain is always larger.
Then?
Larger
than what?
Larger than the target.
Wait, no. Codomain and target is synonymous.
Oh, okay.
Target and codomain are the same thing. Maybe you mean range.
Oh, yeah.
Yes. Range is a subset of the codomain, right? But it could be identical. It might not be a proper subset. So if the function is onto, then function is onto if range is equal to codomain, and the function is not onto if range is a proper subset of the codomain. So there is somebody in the codomain who is not in the range. Then the function is not onto.
I got it. Thank you.
Mm-hmm. Come on, come on.
Question about it's about the what is it? I just forgot what I was gonna ask. Yeah, it's
Well, you have more chances.
yeah, I think I'm trying to remember exactly what I was trying to think about. It was the
Anybody else? Well, this guy thinks. Sorry, I don't have your name.
fine.
Oh, I see. Omar. Yeah, I think.
Yes.
Yeah.
Yeah,
Oh,
it's me, Omar.
hi.
Hello.
Hi. So yeah, somebody wants to ask a question.
Yeah, the updated PowerPoints. I remember the updated PowerPoints. Are PowerPoints updated yet? Like accordingly to how the slides?
No, I didn't upload this set of slides, so I will upload it after the lecture because I'm basically changing the stuff until the lecture. So I will always upload after lecture.
Okay, because last time I saw the PowerPoint, it wasn't really it wasn't updated accordingly, or was it updated?
I think it should be updated now.
Okay.
I mean, yes, yeah. Let me know if it's not, but I think it is. The last week lectures I posted what I spoke with. I think I even toyed afterwards some more to improve them. Yeah, I sometimes do that too, like I will do now because there was a typo.
Uh-huh.
All
It's
right.
more or less the same right now, but it's not really updated just yet.
Sure.
Yeah.
Yes. Okay, guys and girls. Till next time. You have discussion tomorrow. If and sign up for that. I mean, participate in that. And we'll make an opinion poll about like if there's some people who are not serviced by the other discussions, there will be another one. And we'll take a poll on the Piazza on the time. Thanks everyone. See you me Thursday discussion guys on Wednesday. Bye.